Is it? That's the question of this section, section 2 of chapter 7. It's a wave. It is a particle, and it's not really a spectrum, but I thought it was a nice little thing to add here. There is a spectrum that light exists in, so it's not really a wave, it's a particle in a spectrum, but it sounds nice, doesn't it? Okay, so light is electromagnetic radiation. Tro has this figure in there, and I like it. It's great. We're not going to use a whole lot with it, but it's important, I think, to appreciate that there's a magnetic field component and an electric field component, and the two field components are actually perpendicular to each other. I don't know if he says that or not. You can see it here, though. These two fields are perpendicular with respect to each other, and the field propagates in a particular direction. Can you see it going in that direction? And as it does, it oscillates, and so it oscillates to a high magnitude, down to 0, and, sort of a high magnitude, right? But a negative high magnitude, then back to 0, a high magnitude, and so on. So again, we're not going to really, I think, understand this very deeply, but that's what's going on here with this figure, and I think it's good to look at it. Now we're going to look at the aspects of a wave that we are going to care about, and they are here. Actually, one of them is here. We're going to say not a whole lot about amplitude, but the wavelength is a big deal, okay? So we're going to calculate wavelength a lot. So can you see a peak here and another peak here? And the distance between these two peaks is the wavelength. It's the same distance, by the way, as from that node to this node. That's also a wavelength, and of course, trough to trough. Maybe that's a trough, and here's a trough. That's also the same wavelength, okay? So we can wave, it's a little arbitrary to say peak to peak, but that's probably the easiest place to see it. So the wavelength of a wave is an important characteristic that we'll be looking at in this section. I want to have a look at that real quickly. Amplitude doesn't mean a whole lot. All right, so calculate the wavelength in nanometers of red light emitted by a barcode scanner. Can you give me a calculator, pleasure?
Yes, sir.
Thank you. Calculate the wavelength in nanometers of a red light emitted by a barcode scanner that has a frequency of such and such. Okay. You know what? I didn't go over this with you. It's on the frequency. There is a formula, and it's equation 7.1. Equation 7.1 intro, thank you, on page 266. 66. And frequency is given as nu, and is equal to the speed of light over lambda. And that's the formula we're given. All right, so we know that the speed of light is 3.00 times 10 to the 8th meters per second. So our problem here now is to calculate the frequency if it has a wave. The wavelength if it has such and such a frequency. Okay. So the frequency is 4.62 times 10 to the 14th reciprocal seconds, and we're supposed to find the wavelength in nanometers. Can you see that if you've built an apparatus for dimensional analysis, this is going to be easy? Right? There's meters per second, right? You see it right there? So I bring that here. I have to invert it, so it goes, oh no, I don't have to invert it. It's meters per second. There you go, right? And this is seconds over 1, right? Now this is reciprocal seconds, so I've got to take this here. This doesn't get inverted. This one gets inverted. Can you see it? Okay, and if I cross off all these units, now I'm done, right? So without really even getting into how these things exist or why they exist, you see that? Meters, meters, and I'm left with nanometers. So let's put our numbers in here. I think there's 1 billion meters for every nanometer. And this is 3.00 times 10 to the 8th meters per 1 second. And this is 4.62 times 10 to the 14th. It's very important that goes in the bottom, of course. That's an ugly 4, isn't it? 14th. Can you see why it's so important that goes in the bottom? Because this is reciprocal seconds, and this is not reciprocal seconds, so I've got to invert that. So that goes on the bottom, and 1 goes on top. All right, so what does this come out to be? You know what I'm going to do to save myself some calculator trouble? I'm going to get rid of that 9, and I'm going to put this minus 9 up here. And I'm going to get rid of that 14, and I'm going to put minus 14 up here. And 8 minus 9 minus 14 is equal to minus, I guess, 15, right? So this is going to end up being 3 over 4.62 over 1 times 10 to the minus 15. All right, a little bit of a, I don't know if that's a shortcut or not. It's sort of a shortcut, but mostly it's a safeguard. 3 times 10 to the minus 15 divided by 4.62 is equal to 6.49 times 10 to the minus 16 nanometers. Now, I'm not, I got something wrong here, okay? And I know that, I know I have something wrong, and here's the reason why. Because I know that red light is visible in the nanometer region, which means it's going to be between 350 nanometers and 800 nanometers. Okay, and that's described for you, oh, I don't know. Yeah, on page 266, this describes this fact. So I know this is wrong, right? Because that's not between 350 and 800. Now I look back over here, and I see a mistake that I made. I see it right there. Some of you probably caught it while I was doing it. There's not 1 billion meters in a nanometer. That's wrong. That's bogus. There's 1 billion nanometers in a meter. 1 times 10 to the 9, right? That was a mistake. And it was an honest mistake, by the way. I didn't do that on purpose. So what this is going to be is 8 plus 9 minus 14. And it's not going to be minus 15. 8 plus 9 is 17. Minus 14 is going to be 3, right? So, that's crazy. 3. So I'm going to recalculate this. 3 divided by 4.62. Enter. Times 10 to the 3 is 649. 649 nanometers, okay? That was a mistake. You see the mistake I made here? It was right here. I put a billion meters in a nanometer. I don't know why I did that. It was an honest mistake. I got down to the end, and I got a weird number, and I said, wait a second, that's not between here. And I went back and looked for it and found it right there. So it's really 649 nanometers, okay? I'm going to recalculate this. I'm gonna pretend like I did this right. This I'm going to do in blue. And I'm going to say it's really like 1 over 4.62 times 10 to the 14, and that was correct right there, right? Times 3.00 times 10 to the 8th over 1 times 1 billion. That's 10 to the 9 right there, okay? I'm going to do it like that, just to check it. 3 times 10 to the 8th times 1 times 10 to the 9th divided by 4.62 times 10 to the 14th gives me the same number, 649. Okay, so 649 it is, and let's move on. All right, I think we're gonna talk about the electromagnetic spectrum next. It turns out that EM radiation shows up in nature over a wide range of frequencies and wavelengths. So first of all, let's look at this figure. I think it's a helpful figure to look at. There's frequency, here's wavelength, and the stuff that we see, light, is actually in a pretty small wedge of this spectrum. And it turns out that it has a wavelength that's right here. This is where the wavelength is, okay? Right there. Can you see it? Its frequency is right here. Okay? and what's happened is, in order to see this, it's blown out like that. Okay? It turns out that that is about 400 to 750 nanometers, right? When we did a lab experiment looking at spectra, we went from 350 to 800 nanometers, so it's going to be a little darker red, a little further outside the visible range. This is more ultraviolet, a little outside the visible range perhaps, okay? So anyway, it's about 400 to 800 is visible light. That's where visible light is. Anything that's got a wavelength that's shorter than that is going to be UV radiation. And with a shorter wavelength yet, it's going to be X-ray. And with a shorter wavelength yet, it's going to be a gamma ray. Can you see that? And then with a longer wavelength, it's going to be infrared, microwave, and radio wave. Okay? So, cool. All right. So can you see that as the wavelength goes down, this is small wavelength, the frequency goes up, of course, right? So, right, this is a long wavelength. It's going to have more waves that fit into it, so the frequency is going to go up as the wavelength goes down. Okay, so wavelength of different colors, photons with different wavelengths have different colors. All right, so that's what this figure's about. This is also in your book, probably page 267, 266. Okay, wavelength with different photons with different wavelengths have different colors, and red's got a longer wavelength and it's lower energy. Yellow's got an intermediate wavelength with an intermediate energy, and blue or violet has got a higher energy and a lower wavelength yet. I'm not sure if I said that right, okay? I'm not going to go back and try and say it again. You can see from the figure here what the correspondence between color and wavelength is, okay? Now, different brightness are going to be light beams with different amplitudes. Okay, can you see this is the amplitude here? It's described from a previous one. We're not going to make much of the amplitude here in this chapter, but there it is. All right, so let's look. Oops, already did this one. Wait, that's in here twice. Okay, I already did that one. All right, let's talk briefly about interference. I'm on page 268. If you have two waves and they're in phase, and what's going to happen is you're going to get a magnetic or electromagnetic field propagation that is added, right? And can you see that these, you've got sort of maybe a half of height here, let's say half an inch, and then a half an inch here, and then when they go together, it's gonna have a higher amplitude, right? This is constructive interference. When two waves and they're in phase, they're gonna build on each other, okay? When two waves are out of phase, then they subtract from one another. Okay, can you see that if you're adding these two together, they're going to end up being 0, right? Because this is down, so that might be like, say, that's down while this is up, and that's up while this is down, that's down while this is up. Okay, that's called destructive interference. And when the waves are out of phase, they cancel each other. Okay, and I think the last thing we're going to talk about in this section, we've got two more problems to do in this section, but last thing we're going to talk about is the photoelectric effect. And so this is an interesting experiment. I think you're really going to understand this better if you go to page 270 and read it. Let me read it to you for now, but do consider, it's a little bit, I think, a little bit weird. So this is the experiment that Albert Einstein got the Nobel Prize for, I think 1921 or 1915, I forget. So what you have here is you've got some chamber, which is a vacuum inside there, and you've got a metal, okay? So here's the metal, a close-up of the metal, and the light hits the metal, and when the light hits the metal, if it has enough energy, if the light has enough energy, it kicks off an electron, okay? So the electron goes to an electrode, goes down to a battery pushes it out, other electrons, this is DC current. Okay, DC current. That's a horrible looking D, isn't it? DC current. And, right, he's pushing these things out. Okay, so the metal is not building up a charge. It just keeps pushing the electrons back in here. Okay, but the electrons are stuck on that metal surface, of course. They don't want to leave the metal surface, right? So, and the energy with which they're stuck on there, we use a Greek symbol phi. Can you see that? It's a circle with a line through it. This is the binding energy of the electron. Okay, and it's characteristic of the surface. For example, the binding energy of cadmium is going to be different than the binding energy of tungsten or binding energy of, I don't know, whatever else, okay? So the binding energy is the energy that holds the electron on there. Now, the light that's coming in has another energy as well. And the energy that the light has that's coming in, the energy of a photon is h nu. That's a Greek nu, okay? Not a v. This is the energy of a photon. Energy of an incoming photon is h nu, where h is Planck's constant. H is equal to 6.626 times 10 to the 34 minus 34 joule seconds. Okay, 6.626 times 10 to the minus 34 joule seconds, and that has to be given to you. You would never know that. You have to look in the front of your exam or your quiz to use that. Okay, so the energy of a photon is that number times the frequency of that photon. Okay, so now if the photon that's coming in has enough, if it has enough energy to push off an electron, it does. If it doesn't have enough, it just bounces off. That's it. Okay, it doesn't. It's not like it hangs around for another photon to come along, and the two together can can kick it off. No, it's the photon comes in. Either it has enough energy to kick off an electron, or it doesn't. Okay, and the threshold then, if it has enough, here's the threshold. Right? H nu is equal to phi. That would be enough if it's got enough. Okay? Now, if it's got more than enough, then the excess is kinetic energy. So the more that it's got, the faster the electron comes off. All right, so we'll talk more about that in a minute. For now, let's look at this. The threshold frequency is h nu, that's the energy of the photon, has got to be equal to or greater than the binding energy of the emitted electron. That the threshold is if they're equal. That's where it's barely got enough. It's got just enough. Okay. All right. So a nitrogen gas laser pulse with a wavelength of such and such. Okay. So let's calculate this real quickly. We know this that E. I'm on page 271. Page 271. We know that E is equal to h nu, we saw that before, which is also equal to hc over lambda, where I'm taking that nu and replacing it with the one I got on page 266. So these are both true. Okay? And so, if my wavelength is equal to 337 nanometers, and I'm going to write this in meters right away, okay? That would be 337, watch this, nanometers. Nanometers. Okay? And the energy is equal to 3.83 millijoules. Let's write this in joules. And I'm going to rewrite this. Watch this. 3.83 millijoules. Right? You've done those conversions before, but I want to put this in meters and in joules, so I don't have to do conversions later, any weird conversions later. I'm going to go ahead and write a couple other things down that I know. C is equal to 3.00 times 10 to the 8th meters per second, and H is equal to 6.626 times 10 to the minus 34 joules times seconds. Okay, watch this now. I know all these things. And let me also remind you, I said that before, this is the energy per photon. Or I said it differently. I said, watch, let's go to a different color. I said the energy of a photon. Can you see how these two are the same thing? The energy of a photon is the energy per photon. Okay? And I need that because I see the question is how many photons. So what I'm going to do is I'm going to come down here and set up a solution. And the solution, I always start with my answer, right? How many photons? Aha, there's my number. All I got to do is fill that in and I'm done, okay? So I'm going to come up here and I'm going to say this, oh, by the way, this is not the energy per photon. That's the energy of the beam, right? Look at that. This gas laser pulse contains that much energy, right? And so that's not what that is. That's not energy per photon. My energy per photon is going to be E is equal to hc over lambda, okay? So what I'm going to do is set up a separate one now here. Energy of the photon, watch this, is equal to 6.626 times 10 to the minus 34 joule seconds times 3.0 times 10 to the 8th meters per second. Those seconds will cross off over crooked line 337 times 10 to the minus 9 meters. Remember I made that mistake earlier? This is right. This is small, right? Because a nanometer is small, and this is now a small number. I failed to do that earlier, and almost got it wrong because of it. Okay, so that's what this is. I put this. This energy is not supposed to be there. This is supposed to be. The equal sign is here, right? I'm running out of space here. Let's go ahead and calculate that out. 6.626, clear. 6.626 times 10 to the minus 34 times 3 times 10 to the 8 divided by 337 times 10 to the minus 9 gives me 5.899 times 10 to the minus 19. Watch this now. 5.899 times 10 to the minus 19. Watch this now. Joules, watch this, per photon. Right? Big deal. I didn't leave myself enough room here, so I'm gonna write it down a little further, okay? I'm going to go to black. I'm just afraid I'm losing some clarity here in my solution. So let's go this. Watch this. Photons to joules. I know that relationship. There's that relationship there. Agreed? So now I'm going to come up here, and I'm going to have to cross out joules because I'm looking for photons. I already used that. Aha, there it is. There's my joules. And it's not related to anything. It's just that. Back to red now. Okay, so it looks like this is going to be 3.83 times 10 to the minus 3 joules divided by 5.899 times 10 to the minus 19 joules per photon. Joules are going to cross off and I'll be left with photons. And that's going to be the number of photons. I'm going to draw one more picture when I'm done here in case it's in case somebody doesn't like the solution. 3.83 times 10 to the minus 3 divided by 5.899 times 10 to the minus 19. And I get 6.49 times 10 to the 15. 6.49 times 10 to the 15. Does this make sense? It's a big number. Does that make sense? Do I expect a lot of photons or a little? Well, yeah, a lot, of course, right? If you have times 10 to the minus 19, it's less than 1. And if you have 10 to the 15, it's more than 1, right? And we expect a bunch. So that number makes sense. It's probably correct. I'm going to draw one more picture here, and then we'll move on. So just to give us an idea, I'm going to draw sort of a cartoon. Suppose I've got a beam, okay? And it's doing like that. Whoa, crud. Crud. Lost my notes. Where am I here? Okay. Oh, I lost my notes. All right, suppose I've got a beam. You know, it doesn't have an arrowhead on it, right? But you got this beam, and it's propagating through space. And it's got 3.83 times 10 to the minus 3 joules, right? But it's made of a bunch of photons, right? Agreed? Well, each one of those photons has an energy of E is equal to hc over lambda. That's what one of those has. Boom. Right? And so what you've got to do is you've got to take the energy of the beam and divide the energy per photon, right? Because that's the energy for each photon, right? And those are going to cross off, and you get the number of photons. Okay. All right, good. Let's do another problem. I think this is the last one then. Arrange these 3 types of electromagnetic radiation: visible, X-ray, and microwaves in order of increasing, let's say, wavelength, frequency, and energy. Okay, so let's first of all do wavelength. So wavelength goes up here because this is big, right? And this is small. So where are we? Visible light is here. I'm going to put a note here. Visible light is, let's see, 10 to the what? Minus 6. X-rays is here. Looks like that's 10 to the minus 10. And microwaves is here. Looks like that's 10 to the, oh, I don't know, minus 2. Centimeters, I guess, right? Okay. 10 to the minus 6. Now we're supposed to put these in order of increasing. Wavelength is what I'm doing right now. So it looks like micro is going to come first. Or no, that's the biggest, sorry. The smallest is X-rays. And that, because we're supposed to do this in order of increasing, right? X-rays, and then visible, and then micro. Okay? Now you do what I did, but you do it with frequency. And then I'm going to say something about the energy per photon. The energy per photon, remember now, watch this, is E is equal to hc over lambda, which is also equal to h nu. Okay, and so you can see that if lambda is big, E is small, right? And so for energy, it's going to be the opposite. Micro V x for energy.